So without any further ado, Brad Chen from Google.
Thank you for that introduction, Steve. I want to tell you today about a project which actually is just currently moving out of research and into more development phase. It's called Native Client, and it's all about running native code in web browsers. Now, some people ask me, well, why are you telling me about native code in web browsers? Didn't ActiveX already do this 15 years ago or whenever it was, or NP API? And yes, it did, but it didn't really do it safely. And that's really one of the key things that we're going for, is to make native code as safe as the kind of things that people take for granted, like JavaScript. So at a high level, our objective is to close the gap between the desktop and the web applications. Now, one critical area where we see a gap is performance. Obviously, JavaScript is not as fast as the fastest C code you can write. We want to make all of that performance available in the browser. Also, choice of programming language. Just for me personally, I think it's kind of silly that a programming environment tells you you can only use one language. I think people should be able to use any language they want to. And with Native Client, we're taking a step in that direction. And when you give people the choice of languages, then you can also give them the choice of using legacy code that they might want to use. And Native Client in particular is very good at compiling systems built for Linux. So we want to achieve all of these goals while at the same time not sacrificing portability. The system that we're shipping today works in Firefox, Firefox, Chrome, Safari, and Opera, and we're spending a lot of time right now on getting our Internet Explorer support working as well. Now, while we're and also it's portable, you write a single binary module, and it works on Windows, Mac, and Linux. So we're pretty good at browser and operating system portability at this point. Where we're still investing very aggressively and working very hard, and where we haven't really settled on what we're going to do, is instruction set portability. The current system is specific to x86-32. But you know, we're going to work on that. And then safety, like I said, we want to make this native code as safe as JavaScript and other things that people take for advantage. Now, since this is a performance conference, I kind of wanted to emphasize, well, so what does he mean by performance? Well, we really mean all the performance that you can get out of the native CPU. And one of the features that's actually necessary for that is thread support. If you take a look at where microprocessors are going in the future, you're not really going to get much more in terms of performance from clock speed. All the performance is going to come from a couple of hardware features, and one of them is threading. And if you can't take advantage of threading, then you're basically leaving an order of magnitude of performance on the table. Now, we heard some, fairly enlightened commentary this morning about threads being bad. I think that was not exactly the adjective that they used. But I kind of think of threads as kind of like an airplane. Yes, airplanes can be very dangerous. And if you take a random programmer and throw them into the pilot seat, a lot of the time things won't go that well. At the same time, though, if you want to go from, say, San Francisco to Paris in less than a month, the airplane is pretty much the only way you're going to get there. In the same sense, if you want to be able to exploit the full potential of the next generation of microprocessors, threads are kind of the only choice, the only show in town. Like threads are vector instructions. Vector instructions, again, are worth an order of magnitude performance if you can use them. Unfortunately, JavaScript doesn't actually let you use vector instructions effectively. If you want to do a numerical code in JavaScript, if you want to even just do an addition, well, first you have to do 2 procedure calls. One for each operand, and then you can actually execute the instruction that adds the 2 numbers together. So forget about vector instructions. You can't even do a single addition with the efficiency that native code can get. So those are very important performance features. Moreover, we really are doing everything we can such that people who want to write hand-coded assembler, and there's still some cases where it's worth doing, it's not terribly it's not really any more difficult than it would be without native client. So substantially all the CPU performance of desktop applications we intend to deliver. Now, to drive this home in terms of when is this thing actually going to be useful, let me just suggest a scenario. Imagine you have an AJAX application, and part of what it's doing is generating some large HTML tables as HTML on the client. Also, maybe there's some floating point intensive activity. Maybe it's generating an image or something like that. Let's take a quick look at how JavaScript performs compared to C. Now, these are sort of informal numbers, and but just to point things out, so 100 by 40 HTML table, that's actually a pretty good sized table. And if you're looking at V8, then the JavaScript is actually pretty darn competitive with the C. In my informal measurements, I was kind of having a hard time getting a consistent difference. Now, there is quite a bit of variance from run to run, and I'm not going to take the time to go into the details of why. But if you go to a much larger table, 100 by 400, then you'll see even with a really good JavaScript implementation like V8, the native C code can go about twice as fast. And if you go into something numerical as opposed to string processing, something like a Mandelbrot or any sort of physics simulation, then the native code is going to be much faster, in this case about 6 times faster. So these are some scenarios. It gives you some intuition, hopefully, about where these kinds of acceleration techniques might be useful. Now, a couple of caveats before I go on. V8 is a really fast JavaScript implementation, and if you compare this to just about any other browser in the world, it wouldn't really compare. The other thing I want to point out is this was not the first native code implementation. The first native code implementation I did was in C++, and it was actually quite a bit slower than the JavaScript. This native code implementation was carefully constructed not to do any memory allocation. And not a big deal if you're a C programmer, but it's not entirely obvious. So anyways, we want to make things really fast. And what does this mean for the web? Well, we want to enable a whole new set of applications that aren't really possible. You can't even imagine doing these in JavaScript. For example, implementing video decoders. We'd like people to be able to implement their own and deploy them easily. Audio and video synthesis, let alone decoding. We want to be able to synthesize audio and video like you might expect in a game. Multimedia editors, and eventually with a system called O3D, which is kind of a companion to native client and will give the browser direct or better access to graphics hardware, then we'd like to be able to see people do things like high-quality games, CAD applications, the kind of things that you really need to go to the desktop for now. Let me give you a little intuition about how this system is put together now that I've given you some of the background and motivation. Imagine that you wanted to implement a game, and you're going to do some physical simulation in this game. You need the physics to go really fast. Okay, maybe it's computational fluid dynamics or something like that. And so you know you'll never get a decent result in JavaScript. So you've decided to use a native client module. Now, we're going to have 2 models of using native client code, but one of them will be like a plugin. And so you'll specify the native client module, in this case game.nexe, and somehow through a MIME type or something like that, the browser will know that, oh, this is a native client module, and I need to activate the native client container in order to run this thing. So the native client container gets started up, and the browser downloads the native client module, the untrusted code from some random website. Now, suppose for a moment that rather than getting a safe native client module, the application wanted to mess you up, and so it downloaded a native client module that was dangerous. Well, we can't let this succeed, obviously. So the first thing that the native client system is going to do is going to analyze the module it downloaded, static analysis, and figure out if there are any sharp edges. And if it looks dangerous, then we simply will refuse to run it. Sorry, this does not compute. Alternatively, though, suppose that your physics simulation actually follows all the rules that we've established for making native code safe. In that case, we will approve it and fire up the container where the native client module will then be loaded and allowed to start. Now, I kind of like to think of this as being in jail, because there's a set of things that we're simply not going to let the native client module do. In particular, the rules that we create and the container it runs in make it impossible for the native code to directly access the native operating system. And that's how we prevent side effects. There's no way to access the local file system. There's no way to open arbitrary network connections. There's no way to create processes. The only way you can do anything is by executing instructions on the CPU, the limited set, or through the call-out interface provided by the native client system. And in that case, we're responsible for making sure the calls are safe. So we really do intend for these modules to be side effect free, except what can already be done through the browser, through JavaScript, for example. So once our native client module is loaded up and ready to go, we connect it with the browser, and voila, it's now able to do its physical simulation and all that sort of thing at nominally the full native speed available to native code. So let me tell you a little bit more about native client security, because if you are a suspicious sort, and suspicion is very helpful in this kind of thing, this is really the part you should be worried about. We have put a huge amount of time and emphasis in the project in terms of how are we going to take this kind of scary technology and actually make it safe. So some of the steps that we've taken, it's a normal process for Google technology being released externally to go through multiple internal security reviews, and we've done all of them, and we're going to do more. We've also open sourced our system because we strongly believe that the scrutiny of the community will help us find bugs and make the system better. Furthermore, we've written a technical paper about the system and published it in IEEE Symposium on Security and Privacy, which is a pretty good security conference. And you can find that paper on the Native Client website or on the IEEE website as well. Finally, we just finished a security contest where we put cash on the table and challenged the world to find bugs in our system. And it was kind of fun, actually. The contest ran for a little bit over 2 months. More than 400 teams and 600 individuals participated, which is to say they registered for the contest. I have to say that a good number of them were pretty frustrated because only 22 bugs were actually reported for the system. Though reported by basically 7 teams. And just to give you kind of a feel for the kind of bugs we saw, there was one bug in a thing we call the inner sandbox. This is a thing that prevents the native code from executing a syscall instruction. And that, in addition to one bug that was found before the contest, are the only bugs that have been found in that security critical part of the system so far. Apart from that, most of the bugs that we saw were in browser integration, that is our use of NP API or memory allocation problems. I think there was a buffer overrun someplace. But the good news is that we only found implementation errors, no real design problems. And so the set of things that we've done in the security of the system have actually given us enough confidence that we can make this system safe, that is, as safe as JavaScript, that we're now taking steps to prepare to deliver it to a larger community. So today, the native client open source release is NP API plugin only. It only supports x86-32, and it has simple raster graphics. And I'll show you a demonstration of that in about 15 or 20 seconds. The future, we're going to build it into the browser. We strongly prefer to have this system built into the browser rather than delivered as a plugin. We don't think plugins are terribly safe. And we're going to be presenting 2 APIs for accessing it. We're implementing a native web workers API, so like web workers, but for native code, with the same restrictions as web workers, the same relatively safe threaded programming environment. We're also developing revisions to NP API, and we're beginning to work on collaborating with Apple and Adobe on those to make portability and performance enhancements to NP API. We're working very hard on instruction set portability, and we're working again on O3D integration for access to hardware graphics. So let me quickly give you one demo and maybe 2. We have a video decoder that's just an internal system we work on. And this is one of the early codes we ported native client just to see can it go as fast as video. The good news is it was really easy. And quickly, so the 2 highlighted lines are 2 of the, we only had to add 20 lines total. Here's some of them. The highlighted lines are the interesting ones where we're initializing our multimedia system and initializing the video subcomponent. Then we use this call to actually deliver a frame of video into native client. And let me show you, just for purposes of demonstration, here it is, the native client video player. We're not going to watch this whole thing because I only have 35 seconds left. But it works. It's playing video. This is HD quality. I can't remember exactly what the screen resolution is. But the point is that, doing video decoders is entirely within the realm of possibility with this system. The next demo I want to show you, and this will obviously be the last, is a thing we call the native client darkroom. And this is really an active homage to Adobe Lightroom. So far, I haven't really shown you anything interesting. The interesting part is I can actually now do image processing operations on this, like rotate the image. Don't try this in JavaScript. You'll never be able, you'll be doing seconds per frame instead of frames per second. But we'd like to think that someday people could think about implementing photo editing as a completely safe web application. And already we can do this much today with operating system and browser portability. So thank you very much for giving me a chance to tell you a little bit about Native Client. You can read all the source and other stuff on the web, and I'd be happy to take questions. Questions? I can barely see.
Do you have any plans to support PowerPC?
The only instruction sets we're working on right now are 32 and 64-bit x86 and ARM. That being said, the system's all open source. We're determined to make it friendly to other architectures, and we'd be very interested in supporting PowerPC if there was a partner who was interested in helping. It's less likely that we'd undertake it ourselves, but you never know. There's a lot of 20% interest in this project, it turns out, and so maybe we'll get some help from inside. Other questions? Okay, well, thank you very much.